Okay, we got some confirmations. So I'm going to start. Now, before I start, I made an announcement that homework 1 and Julia homework 1 are due tomorrow, midnight. And now it's first time, it might be confusing, we understand. Don't stress over figuring out how to submit it, going through all of that steps, because they're also different. Homework goes through, those are drill problems, they go through Gradescope. So there is a link on Canvas, you can go through Gradescope and you will submit your file. On Gradescope, you can mark each page to be related to what question. Now, this is a standard tool. A lot of courses will use it in coming years, so you'll reuse it again and again. So it's not just one-time learning. For Julia, it's similar to the lab notebooks, but you submit this one. So you can fetch your notebook, you can complete it, and then you can submit it. And then we can pull all your notebooks and then grade it differently from Gradescope. So if you have any question, you find it confusing, just let us know. There shouldn't be any problem. If you made a mistake, you submitted by mistake, it's first time you understand, we'll find a way to fix it, okay? So just make sure you let us know. You can reach out to any of us, you can post it on Piazza, and any other way that you find convenient to communicate with us. Email, office hours. Okay, so is there anything else, Jesse, we wanted to mention beside these two? No, so we're all good? I have a brand new pen. And that should improve your quality of learning from now on. Then I realized actually, the previous pen was broken. Somehow I could use it. All right, so far we learned that we can write a system of linear equations. We have a bunch of variables. They have coefficients. And we have a right-hand side, a bunch of numbers, right-hand side of the equality. And we could turn it into a matrix form. But we never learned how to solve it, actually. Today is the first time that we're going to study a special structure that we can see in some of these equations. Now, we're going to see equations that have that structure. We don't learn how to turn it into these special structures. Later, we will learn to convert it to this form, and we already know how to solve it. And that's the topic of triangular systems.
Hey, Mani.
Yes?
Could you, I think you're not sharing your screen.
Oh.
There's so many things to set up there. I get it, okay?
Well, they say imagination is more important than knowledge.
We're working on it. I like it.
You can imagine what I just said. It doesn't make any sense if you don't have the context. Okay, so now this is also about the role of structures in your problem. And it's always a good thing. If you have some sort of structure, we usually try to exploit that structure to solve the problem faster or make it more scalable, more efficient, improving performance, and so on. And we will see some examples of that too. Now, by the end of today, you should be able to recognize when you see a triangular system, you immediately recognize that, oh, that's just a triangular system. And I know how to deal with it. We talked about the determinant as a function that will map a matrix, a square matrix, to a number. We'll learn two facts that makes the determinant of a triangular matrix, that we will define what we mean, to be very simple. You can even use your hand to calculate it. And we will learn two important topics called forward and back substitution. These are algorithms that we actually solve these systems. These algorithms are used in today's numerical linear algebra libraries. That's how they solve linear systems. Now let's look at this system of equation and tell me what you see. What is it here that is interesting? Or how can you distinguish this system of equation from a generic system that I might give you randomly? Some hints. What type of variables you see in each line?
If you look at the left-hand side, it's like a triangle. It's only one variable, then two, and three.
Well, it does have a triangle shape, right? That is what we're hoping to call them. How about the first line? We only have x1. Oh, you guys, yeah? Okay. That's correct. So you're saying that generally in a system of linear equations, we might have, I don't know, 4x2 minus 5x3 plus. Now we don't have it here. First line, we only have x1. So we don't have this. Second line, we only have x1 and x2. Third line, we have all three of them. That sounds like a very specific way of ordering the equation. It's not just random. How about we try and write it in the matrix form? Now, first of all, we learned that we need to add, it sounds like a trivial thing, but we need to add zeros when we think about matrices. So in the beginning, it's important to internalize this concept that we have 0x2 and 0x3. If the line is not straight, that's my fault. I can't write in a straight line. That's not a structure I'm talking about. 2x1 minus x2 plus 0x3. x1 minus 2x2 plus 3x3. All right. Tell me how to fill in this matrix. This is my A matrix, A. This is row 1, row 2, row 3, column 1, column 2, column 3. Yeah, what's the rule that I can put these coefficients into the matrix?
The first row is 3, 0, 0.
Right, exactly. Because it's already nice and ordered, right? You had some problems that everything was shuffled and you had to rearrange them, but here I wrote it in a nice way. So we have 1, 2, 3, 1, 2, 3, each row. It doesn't matter, you can change. In general, you can swap the equations, it shouldn't matter, but we want to keep it this way here because we have this structure of x1, x1, 2, x1, 2, 3. So it's already ordered, so I can write 3, 0, 0, 2, minus 1, 0, 1, minus 2, 3. And then we could write x1, x2, x3, six minus 2 and 2. And that's b, and that's x. Okay. So we learned this much. This particular example seems very special. I have it typed here in the next slide. What's special about it? Now, first tell me, what was the name for this line? Diagonal. We call this so everything above the diagonal seems to be 0. So you can perfectly classify it. Everything above the diagonal is 0. Everything below it is just some numbers. So if we ignore the zeros, what do we get? We have a triangle. It is in the lower part of the matrix. Hence, we call it lower triangular matrix. In line with our system of naming things. In linear algebra, whatever we see, we just name it most of the time in the obvious way. So lower triangular, we mean there is a lower triangle in the matrix. All the numbers are contained there. It always includes the diagonal, right? So everything above the diagonal, the other way to say it, everything above the diagonal is 0. But because the name is lower triangular, it's easier to think that you are working with the lower part as a triangle. So that's the concept of a lower triangular matrix. Do you have any questions so far? From the beginning, how we write this, AX equals B. How we type the matrix based on the coefficients, and then lower triangular matrices. The question is if there is an upper triangular matrix. The nature is full of symmetries, so there is one. Most of the time in nature we have symmetries. It is not by chance, but we do have it. Let's check the chat. Okay. Now, Jesse might tell you that was my PhD thesis. His PhD thesis was on mathematical symmetry for some physical systems. It's a very interesting topic. I'm continuously learning about it myself. which we will learn about symmetric matrices at some point in the course as well. All right, so let's itemize and document what we just observed in a formal language. So all terms above the diagonal of the matrix A are 0. More precisely, you can use the notation that for every Aij, every entry of matrix A in row I and column J, we have Aij equals 0 if J is greater than I. Let's see. Let's understand this. Let's make sure this notation, you're comfortable with this notation. If it makes you uncomfortable, let's discuss it. Tell me maybe a question you might have, or maybe explain it just. What does it mean, J greater than I? What are the columns or rows that we have this condition?
So whenever the index of the column is greater than the index of the row, it would die with 0.
Whenever the index of the column is greater than the index of row, we have 0. That's correct. It is very helpful to remember that the diagonal was Aij such that I equals J. So an easy way to quickly categorize the matrix for yourself is that the diagonal is the place that the index of row and column are the same. Now, J greater than I, it's got to be one side, right? So we have column 1, 2, 3, row 1, 2, 3. 2 greater than 1 is this one. 3 greater than 1, this one. 2 and 2 is diagonal, it's not, right? The condition is not true. 3 greater than 2, true. For all the other elements, the condition is false, it's not true. So the condition that Aij equals 0, if J is greater than I, leaves us with all entries above the diagonal. Okay? So does that make sense to everybody? You're comfortable with this notation? Okay, so because we're going to use it again to flip the condition for the upper triangular matrix. So once you understand this one, the next one is trivial. It is very helpful to program as well. Once you have these concrete conditions, it's always true, you can turn it into code and program it. All right, so we call these matrices lower triangular matrices. Now, a useful fact is that without proof, the determinant of the square lower triangular matrix equals the product of the diagonal entries. That's super easy, right? So you just multiply 3 by negative 3 minus 1, 3 minus 9. That's the determinant. You might say, I don't believe you. This sounds too good to be true. But you don't have to believe me, but I hope you believe Julia. You can load linear algebra package without a space, define A, compute the determinant, you get the same answer. You can try it with many other matrices too. Now, we're not proving it. I'm giving you as a fact but in the very end of the course, we will talk about eigenvalues. Now, there's a nice theorem in linear algebra that the determinant of the matrix is the product of its eigenvalues, and the eigenvalues of the lower triangular matrix are the diagonal entries, and then you can prove it. It's very beautiful, and yeah?
Is the idea of a triangular matrix both square matrix or also rectangular triangle?
Determinant is only defined for a square matrix, right? So it must be square matrix first, and then if it's triangular matrix, lower triangular, we can use this formula.
I mean, aside from the determinant formula, like we have like a triangular matrix that's also rectangular.
Oh, so the question is, can we have a triangular matrix that is not a square? You can, but it's chopped off at some point, right? It's not in perfect shape. You could have that. But it's not going to be a perfect triangle because you have a rectangle. Now so you don't really call it a triangular matrix, but you could if you want. But it's just not a perfect triangular shape. So what we are talking about are the ideal case, the case that we define the matrix to be that way, it's a square matrix. So you probably most of you didn't follow what I said about the eigenvalues. You should forget about it. And so it's not just coming out of nowhere, right? It's not we tried, turned out to be true, and giving you the fact. But it's not in our interest to go through the proof and all those stories right now. Because we wanted an easy way to check whether there is a unique solution to the linear system. So because of that, this fact is useful for that. But in general, the eigenvalue problem is important enough that people in robotics building decided to name the cafe Eigen. So now you know why it's called Eigen Cafe. And the eigenvector and values is German name. German mathematicians studied the problem, and the name just stuck. I think people felt that they owe enough to linear algebra to name the cafe after some math topic, even though it's an engineering building. That must be the reason. Let's check the chat. All right. And by the way, it's not zero, right? The determinant can be negative or positive. But as long as it's not zero, there is a unique solution. So we are not so much concerned with the sign of the determinant, just the fact that it's not zero. Okay. Now, lower triangular systems and forward substitution. This looks beautiful, triangular system. Can we use it in any way to solve the problem? It turns out we can, and the famous method for that is called forward substitution. Anybody here is familiar with forward substitution already? Yeah, so one member, kinda. But worry no more, I got you covered. So it's very simple. It's how you would eventually solve it. Like if somebody gives you this, lock you in a room and tell you, you can get out when you solve this, you probably eventually would write it like this. If there was no computer. And how would you solve it? Imagine now you're locked in this lecture room It's escape room. We have to solve the triangular system to get out to the next room.
Sorry, I should solve it? Like, try to solve it?
Yeah, maybe just explain.
It's like the first thing I would do is the first line divide by the 3.
Okay, the first thing you do, I'm going to repeat it so people on Zoom also can follow. So now here's an idea. How about we say, divide the first line by 3, 6 divided by 3. Well, it sounds like we solved for x already, right? All right.
And then from there, the next line, first I get x2 isolated, so I divide by 3
Yes.
And if you want to combine steps, you can also replace x1 with times 2 and solve for x2.
So we isolate x2 in one side, and you're saying we can substitute the value of x1 because we already know it, and we get, what do we get? This is the hardest part, arithmetic. You get 2 minus 4, no, minus 2 minus 4 minus 6, 6. That's why we don't want to do it by hand. What about the third one? I'm going to write it here. Same idea, right? Sounds like the same idea works. What's the, somebody says, guess I will stay in the room forever. Don't worry. We are working as a team, so we get out together. Well, what's the pattern? The fact that we can solve it is not that important. The repeating pattern is important because then we can make it systematic, an algorithm. That's what we're after. So we can code it to repeat same thing again and again. We can get a solution out of it. What's the repeating pattern here?
Just keep plugging in, start plugging what you have known. So like if you're on the third line, you're able to plug in the previous 2. So let's say if you're on I, you can sub in 0 to I minus 1.
Right. That's a good way to explain it. We start with the easiest line, right? We start with the easiest one that we can solve it. It turns out that we can reuse what we have to solve the next harder problem. And each time we have more information when we go to the next line, then we know more, and then we can solve the variables one at a time. Every line that we move forward, right? Now, if you consider the line order as the row order, 1, 2, 3, 4, then you probably call it forward substitution. We start from 1 and then we move forward. So we can also solve x3 to be 1/3 of 2 minus 2 plus 2 times 6. What do we get here? 4. Turns out x3 equals 4. So we learned the pattern. I think we're ready to later turn it into a general form. Any number of this should work for any number of variables, right? We don't see any gap in the algorithm as far as we can think of it, because once we start from x1, by the end of maybe line 100, we can solve x100. We should be okay. So this is a very powerful idea, and that's how computers operate. But the catch is that you need that triangular system. I mean, the fact that the life becomes so easy is because we have a triangular system. Then in future lectures, we'll study very interesting algorithm. It's called LU factorization. It's very powerful because we can turn the system into a triangular system. One lower, one upper, and then we can solve it like this. Let's see if our answer is correct. Yes? So we work our way from top to the bottom, and we find the answers using forward substitution. Any questions so far before we move to upper triangular systems? No question on Zoom? Everything is super clear? You feel confident you can solve any lower triangular systems now? Okay, that's good. Now let's study the symmetric version of that. If you flip the matrix, or mirror it by flipping, I mean, if your reflection line is the diagonal line, then you will obviously get an upper triangular matrix. Which, by the way, reflection is also it's a matrix. You can come up with a matrix that models that reflection for you. That's related to your project one, but you will work with rotations. Reflection is another type of transformation. You can model it as a matrix. So you have this object with respect to a line. You can make its reflection using a matrix. So, fun fact, off topic. Okay, so what's the difference between this system now and the previous one? They're flipped. That's right. So the pattern seems to be the opposite of what we had before, because the last line has only the last variable, x3. And then when we move to the one line above it, which is the second line here, we only have x2 and x3, and in the first line we have all three variables. And you probably think already that, well, this shouldn't be a problem because I can just use the same technique. It's just, instead of working from top to bottom, you work from bottom to top. That shouldn't change anything in our logic of how we solve the system. So we put this system in a matrix form. All those stories are true. You have the diagonal, and we have an upper triangle. We have a triangle in the upper part of the matrix. Let's check our rules. All terms below the diagonal of the matrix A are 0. What is different here is that the condition is changed. Previously, we were saying j is greater than I. It turns out if you say I greater than j, you mean the index of the row should be bigger than the index of column. And that results with working with all the terms below the diagonal. Let's verify that. We have 1, 2, 3. 1, 2, 3. Two greater than 1. We don't have any other condition true on this row. 3 greater than 1. 3 greater than 2. These are the only entries that we have I, ij, such that I greater than j. So if this condition is true for all ij, and obviously in this example you have so I is 1, 2, 3, j is 1, 2, 3. They're natural numbers. These matrices are called upper triangular matrices. Now, it's very intuitive to think that the same facts should hold. You can conjecture that, and it's true. All this story about the lower triangular matrix will carry over to upper triangular matrices too. The determinant is the product of the diagonal for the same advanced reason that we will not prove at this point. So in this case, we have 1 times 2 times 3. The determinant is 6. Again, you can verify this in Julia. Define your matrix. We have the first row. One, two, three. Semicolon will go to the next row, right? 0, 2, 1. Semicolon. 0, 0, 3. And the det function here calculates the determinant of A. Okay, so how can we find the equivalent of forward substitution for the upper triangular systems? Any idea?
Same thing as before, you just start at the top, solve for x3 first, and then work your way up.
Excellent. Same thing as before, because you learn lower triangular systems, you can look at this with confidence and saying, I'll solve for x3, then I'll solve for x2, then I'll solve for x1. Each time, I substitute the value from the previous line and isolate the variable that I want to solve for. That was our logic. And not surprisingly, this is called back substitution. You can call it backward substitution, but that makes it too long. You just call it back substitution. So, as you guessed, we solve for x3 first, then x2, then x1. If you do the calculations, you get some numbers for x1, x2, and x3. x1 here in this case, in this example, is 11 over 3. x2 is minus 5 over 3. And x3 is 4 over 3. Okay? Now, let's talk about the generalization. Now, our intelligence is into that logic, is into that algorithm. We don't want to do this by hand. We don't want to do it, and we're probably not good at it to do hand calculation for very large systems. Computers are faster than us in doing repetitive work like that. But at this point, a computer can't figure out back substitution on its own, right? So this is our intelligence that we want to code into the computer. Now, it is very convenient to generalize and make sure the algorithms are true for any cases. It's not just special. Now, sometimes algorithms are special, but in the standard cases, we are after general methods. So let's make sense of the notation you see. Can you explain what you see here? We want to turn what we see as math into words. Explain it. That's usually very helpful if you can write down. When you see math, try to write down with text. And use the equality signs and multiply. That makes it very easy to understand. It's very helpful. First of all, how many rows? N. What is N? A number. What type of number? A whole number. A natural number, a whole number, right? Not negative, because we're counting the number of rows. So the math is saying that you have n rows, that we know that it means n equations. For example, n can be 100, 2,000, 100,000, 5, 3. Can it be 1? Sure, why not? But you don't need a computer for that, right? If you only have this line, you're not going to get paid to solve this. That's the bottom line. Nobody asks you to pay you to solve this. You have a lot of them, then you start getting paid. So yeah, it can be a small number, but we're talking about interesting problems, big problems. So we need to generalize it. So number of rows can be arbitrary, any number of rows. Now, the fact that we have n equations, that implies that our A matrix, if you remember, we have A, X equals B. Now, n rows, it means that the size of the matrix is n by n. Is that right? We have n rows and n columns. What about X? What was the name we gave to X? How many X's do you have? N, right? So we have 1, 2, n. So it sounds like we can stack it into an n vector, right? A column n vector. That was the name we gave it. Not super important, but this is a vector with n entries in a column. And B is also n by 1. Now, we are claiming that this is a general case of a triangular system. Let's verify that claim. Why is that? This is a triangular system, and it's true for any number of equations. We want to verify that claim. But before that, what does it mean, these dots and all the crazy stuff I'm putting here.
We could be simply hard and any number because the equation that you want to need. Those dots will just represent that.
Right. So because we want to have as many equations as we want, dots are, it's saying that repeat what you see in the pattern that you see. Like it's, so that means that there will be a third equation. Then you will have a 3, 1, x1, right? Plus a 3, 2, x2 plus a 3, 3, x3 equals b3. There is a fourth line, there is a fifth line, and you can just keep going, and you reach the last line. So that those vertical lines, it means that the left-hand side is continuing like that, and the right-hand side is going to be b1, b2, b3, b4, so on. So there's nothing complicated here. That's just a notation that we use for convenience because we don't want to write all the lines. We can't write it. What about the horizontal line? This dot, dot, dot that you see here. Yeah, make a wild guess.
Just thinking, same thing, and continue all the way from 1, or N1 all the way to N.
Same concept, exactly. So we want to continue from 1, 2, right, 3, and n. Now, this line would not fit on my slide. If I want to write 1, 2, 3, 4, 5, 6, really unnecessary to do that. So dot, dot, dot means you have all of that, and then the last one is nn. It will end with that term. Okay? All right, we get this out of the way. That's the vertical line. That's the horizontal line. What about this equality sign with a line through it? Doesn't equal, not equal, right? Well, if that's equal, it's very intuitive to call this not equal. We cross it. What it says is that a particular coefficient is not 0. And that particular coefficient seems to be the one that is on the diagonal of the matrix. Because you have 1, 1, 2, 2, and n, right? Now, it sounds like we are enforcing a condition that if the coefficient that is on the diagonal of the matrix should not be 0. Now, from everything that you learned so far, make a conjecture why we need that.
The determinant is equal to the product of the diagonal. So if one of the values on the diagonal is 0, then the determinant is 0.
That's a perfect like formal way of justifying this condition. We just learned that determinant of a triangular matrix will be the product of its diagonal entries. We also learned that if the determinant is 0, there is no unique solution. So if any of the diagonal entries will be 0, the determinant will be 0, right? So it sounds like that's not what we want. We won't be able to solve it. And a more practical level, to see what happens in practice if that's the case. So we just said that the determinant of A will be A1, 1 times A2, 2 times A and n. If any of them is 0, it will make this 0. We don't like that. And the reason we don't like it because now what if, well, the meaning of that is that here, this is 0, right? So we're going to have 0x3. We're stuck. We can't do anything. Because our solution was that we're going to solve the very first one in the bottom, the variable that is alone in the bottom for upper triangular system, or the one that is in the first row for lower triangular system, and then we work our way from there. Now, if the coefficient is 0, which happens to be in the diagonal of the matrix of coefficient, we cannot solve for that variable, and we are facing with two variables in the next equation. So we can't solve it if that happens. So it's very important to satisfy that condition. That's why we write it down to make sure it's part of the generalization. Okay, so we clean this up. Now, hopefully this will look less intimidating, if it ever was. So many symbols on one page. But it is just telling us there are n rows, there are n equations, there are coefficients. The first one we have x1, the second one we have x1, x2, the third one we have x1, x2, x3, and the nth one we have all n variables. On top of that, make sure in each line the coefficient of the variable that we wish to isolate and solve for is not 0, because we're going to get division by 0, or it's just a variable will disappear. Sounds like if we have such a system, we can build a general triangular system, lower triangular systems, with non-zero determinant, which means unique solution. Let's write it down. As the way we solve it using forward substitution. Now, what you see here, it is exactly what we did with numbers. I first solved for x1, then x2. It is exactly the same one, but we write it down using symbols that we have to keep it general. So, we don't like division by 0. We make sure that is satisfied. In forward substitution, we solve for x1. x1 is the right-hand side, b1, divided by coefficient of x1. If you isolate x2 from this second equation here, right? What do we get? We get, I write it here to make sure we do at least one of them. Okay. Oh, sorry. At this point, we already know x1. We want to solve for x2, right? So x1 is b1 divided by a1, 1. a2 to x2 equals b2 minus a2, 1, x1. So I guess we agree that I can divide both sides with a2, 2, and that will make it 1, as long as it's not 0. We don't get division by 0. So it seems like, can we generalize it? What would be the last line? in simple words? What do we do? Move everything except the variable we want to isolate to the other side of the equality. It will negate the terms, right? So we always end up with the right-hand side minus everything else except the variable that we want to solve for. And then there is a division by the coefficient of that variable. So that's all that's happening. So it's going to be very long and bulky, but it is really just simple manipulation of moving them to one side, dividing by the coefficient. It gets longer and longer as you go to, you move forward to the final equation. So that's why the final one, you see, it's, again, the right-hand side minus everything else up to xn, because xn is the one we want to solve for, divided by its coefficient, assuming it's not 0. So the rule seems to be true. We can work with indices and then always define it that way, from line 1, 2, 3, and so on. So do you have any questions so far for the general case? Because what you will code in your homework is, at least the most important one, is that it's not about solving a triangular system that we give you. That's not the point. The point is you can write a program, say a function, that when you define your coefficients and b, right-hand side, if it's in triangular form, it will solve x for you using back substitution or forward substitution and give you the answer x. And it should work for any number of variables. So you want to have that function, that code, and then you can reuse it for every problem that you have. So that's the goal. So to understand that, you need to think through the steps, the logic, the algorithm, so we can turn it into code. And it should work for any system. So that will be your homework. So now, is there any part of it that you would like I repeat or talk more about it? Yeah? Can you repeat it, please? Yeah. It's very difficult to hear. Two masks. Oh, okay. Very good question. It turns out two masks will block your voice. That's what we learned. It's very interesting. Have you taken physics, mechanics, something like that? Sounds are mechanical waves, right? It goes through medium. As the medium gets thicker, we'll absorb the energy of the wave. How many masks will it take? We don't hear you at all. Experimental physicists will do that to try it. Jesse says N. That's a theoretical physicist. N can be anything, right? That's what we do here. We think like a mathematician. There are n equations, N can be anything. We will make a generalized algorithm. We will not try for different numbers. So can you hear somebody in vacuum in space? You can't. Some of you know there is no medium for the sound to travel. And we had to accept it. We never tried it, any of us. Okay. Enough off topic. The question was, how do your double masks distracted me. How do you code this? This is a good question. You're writing some math notations. It doesn't make any sense to code it in Julia like that. Well, the root of this question is that I cannot have infinite lines in my program to handle any number of equations. That doesn't make any sense, right? When you put dot, 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 vertically, horizontally, you're telling me it could be any number, and I need to do it for arbitrary number of times. How can I write a general code that knows that? This is impossible. And you're right, it is impossible if you want to hard code every single line. But what we will learn in Julia Lab is that there are techniques called, is it flow control or control flow, trippy? I never learned this. It's called control flow. Now there are some, every language usually has these tools. There are some keywords like for, while, if. So using some indexing and these control flow keywords, you will tell to create a loop. Repeat that loop, for example, for n is the input, right? Which is the size of your number of equations. Repeat this general rule for these for this variable for certain indices, right? And stop the loop when you've done it n times. So then you won't need to write it n times. You write it ideally one line. Now, there might be more than one line because you might do other things to prepare. But that for loop will repeat it. There's a link in chat. You can read that. But this is a very important topic that should be covered in the lab, right? So you learn how to use control flow and keywords in Julia. Now, obviously, these equations are not enough. You need a line that tells you how indices are changing as you move forward from 1, 2, 3, 4, based on number of equations. In other words, you need to write it in terms of I, j indices, and these are changing based on what row and column you're dealing with, right? So to answer your question, we cannot do this, right? We need more programming skills to convert this to algorithmic implementation. So what I have here is not an algorithm. This is just a general way of writing it. When we have an algorithmic implementation of it, an algorithm is something that you have input, you repeat, you have some statements, you do something, and then you have an output. And you can code that. It's a pseudocode. Using different languages, you can code that in the computer. That's very usually straightforward to convert it to that language if you know the syntax and programming in that language. So I leave the algorithmic implementation of this for the lab, not for today. That's a very important topic, which is why we call this course Computational Linear Algebra. We want to learn that side of it too. We will not stop here. What about the other case? We had upper triangular case. In the upper triangular case, the final equation was the easiest one, right? So we can solve for xn divided by the coefficient, but the rule is the same. Move everything else, everything besides the variable you want to isolate to the other side, and then divide by its coefficient. But we do back substitution. We start from the bottom line of the equations, and then we move up. Similar to the previous case, the reason we don't like zero coefficient on the diagonal because it will make the determinant 0. Same story for the lower triangular case. Besides changing the structure from lower to upper, there is nothing more special about this case. It is exactly the same idea. However, you will need a different, probably, function to implement for this case. So you need a forward and backward routine. So we solve our equations in the generalized way using symbolic notations. And as before, we still have these dots. We still need an algorithm. Again, in Julia Lab, you will work through that. And so from here, what you should be able to do, so this lecture and the lab that will follow and the homework should enable you to recognize triangular systems, being able to program forward and back substitution, and reuse that code. And in fact, you will reuse it in the future projects. Now, you could use the one that is in Julia, but we don't want to just make it fully black box. You want to implement and reuse yours. After this course, right, let's say you're working on a project. Now, you know what you're doing. It's OK. You can just use the library. You do not need to re-implement what's available to you from the library, but it's important to understand how these things operate. Because when something goes wrong, you're able to judge what you see. Okay? So that's it for today. Do you have any questions so far? From any part? Lecture 1 to here? Anything we talked today?
Just more, it's not really a question of topic, but when will the Julia homework be released?
When Julia homework will be released? Julia homework is released. No, homework 2. I think.
So the day we submit it is the day we release the next one.
Okay, to repeat it for people on Zoom, the day you submit your current homework, which is now homework 1, it's due 11:59. Right after midnight, you get the other one, so don't go to bed. Once you submit it, start the next one immediately. But you don't have to submit it 11:59, right? If you can solve it, ideally earlier, and make sure keep your sleep on schedule. But typically, we set it end of day. Especially some people might be on different time zones. But anyway, so next time, So there is a code in chat. That's what you will learn in Julia. For K, from 1 to 9, solve homework, end. If you understand that line, you can solve your homework. So next time we'll talk about matrix multiplication to make sense of A, X, B, because we're just putting them next to each other, it doesn't make any sense. We'll talk about that we can actually multiply matrices and vectors. So for that, please take a look at chapter 4 for the next time. Okay, good luck with your assignments and homeworks. I'll see you on next Monday.